Hi, my name is Juan Pablo Robles, and I'm a robotics engineering student at the University of Guadalajara in Mexico. This summer, I've been part of the RISC program at Carnegie Mellon University, working in the shared lab, under the mentorship of Dr. Melisa Orta Martinez. My project focuses on improving non-visual interaction with digital content for blind users, using a low-cost technologies. So, why is this important? Exploring spatial aspects of digital interfaces remains challenging for people who are blind. Current solutions often rely on expensive graphic tablets, making them inaccessible for many users. So, this project proposes a low-cost tactile mouse that allows for spatial navigation using haptic feedback, aiming to make digital interaction more inclusive and scalable. So, what's new in this version? For this version of the system, we implemented a new absolute positioning method by fusing data from an optical sensor and an IMU. We also migrated the system from STM32 to ESP32, mainly because ESP32 offers better versatility and a larger developer community, making it easier to integrate new features. So, this new feature connects directly with an existing GUI developed in processing. So to provide haptic feedback, the systems offer two different channels. First, we have a delta robot that creates physical forces to guide the users on the GUI. And second, we have an haptic globe. This haptic globe has LRA's actuators placed on the hand to provide cursor position feedback. So how does absolute positioning works? The absolute positioning is handled in processing. So we read the relative movement from the optical sensors. And then we rotate those components based on the current orientation of the mouse, which we get from the IMU's yaw angle. This allows us to compute the absolute position on screen, independent of how the device is rotated. But what haptic feedback options do we have? As mentioned earlier, we offer two haptic feedback modes, one through the Delta robot and one through the globe. The globe has directional LRAs and vibration cues on fingers and palm. Also, we have the 3 degrees of freedom delta robot, who provides physical resistance. So with that, we can have modes that simulate springs, oscillations, and directions. So what are the delta robot modes? The delta robot supports three principal haptic modes. The first one is fixed point mode, which simulates a virtual plane with a configurable stiffness. Second, we have the directional oscillation mode, who moves the platform horizontally in a given direction, helping to guide the user. And last, we have the vertical oscillation mode, who moves the platform up and down, acting as a cue to indicate reference points in the GUI. So, what is the GUI? The GUI is a graphical user interface. This GUI was developed in processing and allows drawing shapes like circle, triangle, and rectangle, so we can show blind people how are these forms and how to trace them. So, the GUI sends commands to ESP32 for haptic feedback, and we can have real-time interaction with position plus the feedback. This is our actual GUI where you can see the figures that we trace, also the shape selection in the left side, which are circle, rectangle, triangle, and some options to like the base of the circle, the height of the circle, to start tracing, and some kind of things like the speech for the blind people, because this interface is not like for them, it's for the people that are gonna help them to start using it. So we have experimental evaluation. To evaluate the tracking accuracy, we move the device 1 centimeter at a time, recording the accumulated pixel movement in each step. This was repeated under different yaw angles, 0 degrees, 30 degrees, 60 degrees, and 90 degrees, to compare the real motion against an ideal reference. So the result was a minimal deviation and a high repeatability. Now we are on the haptic globe evaluation. For the globe, we tested two different LRA layouts. One configuration, place actuators on the thumb, middle finger, pinky, and palm. The other, place all LRAs in the palm only. This allows us to compare directional perception and user preference across both setups, which the feedback from the distributed LRAs improved the confidence in the people who tested. In conclusion, and to summarize, fusion-based tracking enables reliable absolute positioning. Tactile feedback improves the spatial awareness for blind users, and the Delta robot adds rich physical interaction through force feedback. Overall, the system is low cost, modular, and effective, with a strong potential to further development and real-world use. Some future work include have the fully integrated version, conducting long-term user studies, refining the globe and delta design, and testing with blind people. Also, I would like to thank to Carnegie Mellon University and the RIS program, especially Rachel Borsin, John Dolan, Dungu Lee, and Dr. Melisa Orta. Also, I want to thank my university, CUSEI and Universidad de Guadalajara. Also to Rector Marco Perez and Carla Planter. Thank you.